Hi again, everybody. Chris Tisdale here. Thank you for joining me. Now, in this presentation, I'm going to respond to a few requests from students about some calculus revision videos. So I've been looking through some of the practice questions, and I'm going to share a few examples that involve inverse trig functions and inverse hyperbolic functions as well. So let me share my screen with you and we can have a look. Okay, so here's a question. Let me just make it a bit bigger. There we go. Here's a question involving the derivative of arc sine or sine inverse. Okay, so there's a lot of words here, but let's try to understand what's going on. Okay, Yasmin is trying to understand why the derivative of this equals this. But Yasmin skipped the lecture on the inverse function theorem. And so the following method is suggested. For x between 0 and 4, we consider a quarter circle. So in this case, R would be 4. With the points here, here, and here. Okay, and the angle theta is in here. All right, so what are y and theta in terms of x? Okay, and then they give you a hint, no parameter other than x may be used in your answer. All right, so let's look at y. So y is basically the height in this picture above this point here, okay? So this part of the circle, it's x squared plus y squared equals 4 squared because the radius is 4 in this example, and it's the top half, right? So y is non-negative, okay? So here I've got this expression, right? And then what is theta? Well, theta is just basic. You can do it using basic trig. Okay, so let me draw you a little picture, and I can show you what's going on. Okay, so here, all right. So in this example, we've got this 4 and 4. Okay, and this is part of the circle x squared plus y squared equals 4 squared. And of course, y is greater than or equal to 0. So we can rearrange that. It's the positive square root, okay, because y is non-negative. Okay, well, what about this other part? You've got an angle here, and you've got, this is sort of, in this picture, that's x, right? So if I sort of copy that over here, now it makes a bit more sense, hopefully. That's 4. So this little triangle here is what we are concentrating on, at least in my picture. Okay, so by trigonometry, okay, sine equals opposite over hypotenuse. So theta equals arc sine or sine inverse x on 4. Okay, so this is where our two answers come from, and that's one way of justifying it. All right, let's look at part B. What is the area A1 of this sector? So it's the green area. Okay, it's the green area. Okay, well, let's remind ourselves of the area of a sector. Oh, so here we go. I think I'll just kill that email so you don't keep reading my email. All right, so let's say it looks something like this. Okay, that's a sector and it's got, a radius and an angle. So the area is just a half r squared times the radius. So in our case, the radius is 4, and theta is here. Okay, so it's half times the square of the radius times theta, and theta is from up here. Okay, so that will be part B. All right, you then define a function via this integral. Now, this integral is basically the area in the quarter circle, or the quarter disk, if you like. Okay, from here up to x. So, yeah, sorry. Let me say that again. The area here will be A1 plus A2. Okay, it's not necessarily the whole quarter disk. All right. So by adding the areas of the sector and the triangle, you tell Yasmin that, okay, well, that's what we got up here. And then that's the area of the triangle, okay? So it's got base, little x, and it's got height, y, and we work that out over here. So it's half the distance of the base times the perpendicular height. So that's where the second part comes from. All right, part C. Finally, using part B, okay, they're basically asking you to differentiate capital F. Okay, so you can see down here, this is the derivative of this, and then this whole mess is the derivative of that. Okay, so you just got to choose the right thing. So it's continuous, and we know we can differentiate integrals using the first fundamental theorem of calculus. There's a few other ones, but that's the one we want. Okay, so then they go through and do it. Now, it's kind of interesting here. If you couldn't get this, it's actually here if you integrate it, right? You can kind of put it together. So you can kind of work backwards if you're desperate in this one. All right, lastly, part D. Yasmin is satisfied that this method works for positive values of x. We can manage x equals 0. What happens when x is negative? Okay, so you tell them that since arcsine is odd, then its derivative is even. So let's talk about that for a minute. And the conclusion is the above formula here holds for negative x. So if I bring my Maple screen in, here is a plot of sine inverse or arcsine. You can see it's odd. And then here is the plot of this. Now you can see this is the derivative. You can see the derivative has a even relationship, right? It's even. So we can basically say there that because the derivative's even, that this is true. Okay, so whatever works for x, whatever we have for x, we can extend it to negative x. So that's what we have. So let's check. Let's see if we get the green. Yes, 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 and yes. Woohoo! All right, so let's do another one. I'm just going to do the calculus. Okay, here's another one. Here's another one. All right. So Let me make this a little bit bigger. Okay, you have a friend, Eric, and we're looking at this integral. Okay, and then there's some bits wanting you to integrate it and compare it with this integral. Okay, that's basically what this question is asking you. So let's work through it bit by bit. All right, you first decide to complete the square. Now, completing the square is an algebraic technique where it's something squared minus something else squared in this case. So you take half the coefficient of x, so 14 in this case. Take half of it and you square it, and you add it and take it away, and then you factorize. Okay? So that's how you complete the square. If you expand this, you'll get this. Okay? But the important thing is this is 7 squared. Okay? So something squared minus something else squared. Okay, so now they're saying, okay, make a substitution. So replace this with this thing and make a substitution. What do you get? Okay, well, let me make some notes there. So just give me a second. Okay, bring that over there. Okay. All right, so they're saying let u equal x minus 7. So we're not going to change the differentials here. And this, of course, is root 7 squared minus x minus 7 squared dx. So you can see what's in here is our substitution. And so this is going to be du over 7 squared minus u squared. Okay, so that's our new simpler integral. So let me bring this back in now. Okay, and that's what I get here. Okay, great. Converting back to the original variable x, you get that the integral here is something plus this. Well, you can integrate with respect to u and then do that, or you can just put it into maple. Let me see if I can pull this across. So here, so this is the original one. This is the simpler one. And of course, if u is x minus 7, then you'll get some simplification. Okay. So that's where this comes from. Da, 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 da. All right, so that's the first part. Now, Eric has a different method with a seemingly different answer that tells you, okay, so let's go with this format and see what happens. Okay. All right. So they've broken up the square root into a product, which is fine, and then substituted v equal root x. Okay. So let me pull that over here and see if we can do something. All right. So also, we've got this. And we're going to let v equal root x, and x is going to be non-negative here. Okay. So if that is true, dv equals 1 on 2 root x dx. Okay. So I can take this bit and sort of get dx if I put a factor of 2 in there. And it's going to be something like this. So this bit, I can sort of do a 2 and a 2 there, right? That gives me that. So I'm going to get 2 over, now 14 minus x, that's going to be 14 minus v squared. Okay, because if v equals root x, x is going to be v squared. Okay, so if I go back to my answer, that's what I've got. And that's exactly what I've got. So that's going to be Eric's integral in terms of v. All right, converting back to the original variable x, we're going to get this new expression g. So what I've done here, and let me just pull over my my maple. So I've just put the integral in here, and I get that. And of course, v equals root x. So you can simplify this a little bit. Okay, so that's what we're going to get there. All right, lastly, you and Eric notice that on this interval, where both f and g are defined, so that there's g and there's f, right? They look different. That's the thing. That's one expression for the integral. That's another expression for the integral, okay? There must be a constant c such that this is true for all x. What is the value of c? Okay, so g and f only differ by a constant on the whole interval. So this constant stays the same, doesn't matter what x is, okay, in between 0 and 14, okay? So what I've done is I've just gone, okay, g minus f is going to be my constant c. And I can just plug in or substitute any value of x between these ranges. So I've taken the simplest one and I've gone, right, c is just going to be this evaluated at x equals 0 minus this at x equals 0. Okay, so I've done that here. Now, Maple can't simplify that, but it doesn't matter because it's still the correct answer. Okay, if I go over to Maple here, I said Mobius can't simplify it, right? I've just copied and put it in there and you get pi on 2. Okay, so you can simplify it if you want to, but I've chosen not to do it. Explain how you found the value of c. Well, let me make this a bit bigger. Okay, so maybe one sentence, substitute x equals 0 and calculate the difference to find the value of c. That comes from here and it works for all c. Okay, let's check to see if we actually got it right. Okay, yes, 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 yes. And this will be marked by a human. Okay, everybody. Well, that I'm pretty sure is all of the calculus questions for 2024 term 2. Okay, so I hope they're helpful. Good luck with the exam. And yeah, I'll hope to see you soon. If you have any comments or questions, you can put them in the comment section. All right, folks. Thanks a lot. Bye.